All right, let's move on to our topic today, which is climate change. Now, climate change is a word that you hear all the time. It's almost like a buzzword. They talk about climate change in the news, and it's a huge topic when we're talking about the environment, when we're talking about the ocean. But what is it? All climate change is it's a change in our Earth and like our temperature and our rainfall over a very long time. So usually you can't even really tell what is happening with climate change unless you have a really long study. I think the minimum to be able to tell is like 30 years. So it's just a gradual change in our Earth and what our Earth produces, like I said, rainfall and temperature. So a lot of times I hear people say weather and climate change interchangeably, but do you guys think that's right? Do you think that weather and climate change are the same things? So answer that below. Are weather and climate change the same? Awesome job, guys. So a lot of you got that correct as well. No, they are not the same. So like I said, climate change is that like very long-term study of how our Earth is changing, where weather is very so we can get the weather forecast for tomorrow and for 10 days out. So it's what's happening right now with our Earth and the precipitation around our Earth. Like I said, we have the Weather Channel. They can tell you what's happening or at least predict what's happening today, tomorrow, up until 10 days. Where climate, you really can't do that. It's much more long term. And now, even though climate change kind of a lot of people think to do with human driven problems, that's really not the case. That's a very big misconception. Climate change has been happening on Earth for as long as we know, even before humans were not on our Earth. Now, the other thing is though, is that since humans have found more ways to use energy, this is how our climate and our global temperature has been changing drastically. So just to go over that again, climate change has been happening way before humans, but the change or the rate of change has gone way, way up since humans started using energy and fossil fuels. This time period is also known as the Industrial Revolution, which happened about 150 years ago or so. And so here is kind of a graph of what I'm talking about. So when we say climate change and what's happening into our world today is that temperature is increasing and precipitation is increasing. So both of those things are going way, way up. So if you guys see the year right here and how in the 1600s, 1700s, even way before that, it was somewhat steady. All of a sudden we get to the mid 1800s and our temperature is rising up like crazy. There's that very upward trend of our global temperature. So things have been getting hotter and hotter and hotter, and there's a few reasons why that is happening. So my next question for you guys, I have another poll question for you, is what do you think, and I kind of just briefly mentioned it, what do you think climate change directly affects? Do you think it affects temperature and rainfall, earthquakes and wind, temperature and gravity, or rainfall and wind? And when I say rainfall, it's the same thing as precipitation. So snowing, hailing, just heavy rains, any of that kind of stuff. So temperature and rainfall, earthquakes and wind, temperature and gravity, or rainfall and wind. Which one do you think climate change directly affects? All right, guys, about 73% of you got that correct. It is temperature and rainfall. So climate change affects how hot our Earth is getting. It's going up continuously, and it also affects rainfall, and rainfall is also going up continuously. And just because it affects those two things, this might not seem like a big deal, but it really, really is. Now you might ask, how do we know that these things are happening? Why do scientists think that our global temperature is going up or our global precipitation is going up? And one of the key indicators of how we can tell that these things are happening is evidence we find in glaciers. So my next poll question for you guys is, what is a glacier? Is it a slow moving mass of ice, or is it a fast moving body of water? So a glacier is a slow moving mass of ice. And they are usually made by when you have land. So they're like a moving mass of land. And it snows and snows and snows. And over time, that snow compresses so hard together that it turns into ice. And like I said, these glaciers are always moving really, really slowly. Now, it's kind of interesting to think, how can a big block of ice tell us more about what our Earth is doing? Well, there's a few different reasons. The first one, if you guys can see this picture, this is a glacier in Montana. This is from 100 years ago. Do you guys see how much more snow and ice is in this picture than this picture from 2012? That's because since global climate change is happening and temperatures are rising, our snow and our ice from our glaciers is melting. So the second way that glaciers can tell us a little bit more about our Earth is actually getting measurements from the core inside of them. So scientists basically drill a really big hole in these glaciers, just like this in this picture right here. So this guy, he took a huge sample of an ice core. It's basically just a cylindrical piece of ice going all the way down the glacier, is basically as far as it can go. And once you get this ice core, you can look at the snow and see a ton of evidence of how much oxygen and how much carbon dioxide is in that core. And it'll give you clues as to how hot the Earth was and how much carbon dioxide was on the Earth from years and years and years ago, when that ice was actually like on top of the glacier. So just from glaciers melting and also those ice cores, those are two ways that glaciers can actually show you what our Earth is doing and how our temperatures have changed from over time. Now, climate change, when we talk about it, especially in recent years, is really, really bad. There are tons of ways affecting humans and animals and our environment around us. First of all, like we just talked about, those glaciers are melting, our ice caps are melting, which is actually causing our sea levels to rise. Not only that, but just our two ice caps are at both ends of the Earth, they're also melting. This rise in temperature causes abnormal seasons for blooming flowers and for animals to mate and for plants to bloom. Also, the intensity of that rainfall is increasing storms like hurricanes. It's causing way greater flooding in some areas. And also that change in temperature is causing things like heat waves and forest fires and really, really bad droughts. And finally, and this is what we're going to talk a little bit later, it's also causing the ocean to acidify, also known as ocean acidification. So those are just some of the things that are happening to our Earth that are really not good. And on top of this, I was saying earlier, Earth has gotten more hot in the past 5 years than it has gotten in the past 5 centuries. So it's speeding up at an alarming rate. So all these bad things are happening. Like I just said, there's just really severe weather going on in places, flooding, droughts, bad hurricanes. And so now I want to talk to you guys a little bit more about what's causing all of these changes. So there's something called a greenhouse gas. Have any of you guys ever heard of a greenhouse gas before? Do you guys know what a gas is? So you have a solid, a liquid, and a gas. So it's just these little molecules that are up in our air. So a greenhouse gas are these gases that are up in Earth's atmosphere. Now, if you guys have ever heard of a greenhouse before, it is a glass window building that you put plants inside. And that glass window building helps your plants grow because sun will go into the building. Your plants will grow because they obviously need heat and sunlight. But since they're in that glass-filled building, the heat will not escape. And so just like how we would grow plants in a greenhouse, this is something very similar actually happening to our Earth from greenhouse gases. So a few greenhouse gases include water vapor, carbon dioxide, methane, just to name a few. I drew a little picture for you guys to show a little bit more about what a greenhouse gas is. So here is our Earth right here. Okay. And then that little dotted line right here, that shows you where our atmosphere is and where all of those greenhouse gases are. Then we have the sun right here. And the sun brings these heat waves to our Earth to warm it, which is a good thing. And as the sun is warming our Earth, these and this heat actually gets trapped by our gases in our atmosphere and heats our planet. So greenhouse gases are actually a really good thing. If we didn't have them, our Earth would be about 60 degrees Celsius colder than it is right now, which is pretty much means that there's going to be freezing temperatures everywhere. So we do want greenhouse gases. The problem is that we are creating way too many of them. And a lot of the reasons that too many greenhouse gases are being produced is because of humans. So greenhouse gases, the number, well, actually, I have a little poll for you guys. So like I said, some of the greenhouse gases we have is like water vapor, methane, ozone, carbon dioxide. So out of these greenhouse gases, which do occur naturally, humans actually produce a lot of one of them. So do you guys think humans produce the most of carbon dioxide, Earth, methane, or hydrogen dioxide? Which one do you think humans produce the most of? Right, guys, really good job. So that answer was carbon dioxide. Yeah, humans in 18, we emitted, which means produced or let out, 81% carbon dioxide. So methane was 10%, nitrous oxide 7%, and fluorinated gases, or like the rest of them, were 3%. So carbon dioxide, 81% is how much humans were producing. So a few of the ways that humans can produce this carbon dioxide is basically anything that uses energy. So playing video games, turning on a water faucet, turning on a light, using fossil fuels that come from factories, even like the meat industry. So producing a ton of red meat you need just so much energy for that task that even something of that sort causes you to use a ton of energy. So these are all things that humans are doing that are causing our carbon emissions to rise. So now we're going to go back to a little bit of chemistry. I'm going to give you guys some definitions of some chemistry terms to hopefully make the next activity a little bit easier for you guys. So what I was saying earlier is that all these greenhouse gases are molecules. So if you guys remember, molecules are just any combination of atoms that are all connected together. Let me find my other little worksheet for you guys. So this picture right here, this little teeny tiny circle right here, that is an atom, or the smallest form of matter you can find on our Earth. A molecule is when we have two atoms together. A molecule can be 2 atoms, 3 atoms, 100 atoms. However many are bonded together, that creates a molecule. Now, whenever I say the word bond, it's basically just meaning that these 2 atoms are connected together. So a bond just means that they're connected. So we have an atom right here, a molecule right here, which is like 2 of these atoms. And then finally, we have a compound. Now, a compound is still a molecule, but it's when we have completely different atoms bonded together. So for example, and Miss Dora showed you guys this the other day, this compound right here is H2O, or also known as water. So the H over here stands for hydrogen. One hydrogen is an atom. This hydrogen is an atom. This oxygen is an atom, but all 3 of these atoms are bonded together create a compound. So hopefully that helps you guys out a little bit. I know it's still slightly confusing, but we're going to go over that again very shortly. So I have another poll question for you guys. Is water, or H2O, an atom, a molecule, or a bond? Is H2O an atom, molecule, or a bond? I know that chemistry is a little bit confusing, so don't feel bad if you got it wrong, but water is a molecule. So looking back at that picture, an atom is the smallest thing on Earth. A molecule is 2 atoms bonded together. And so H2O are different atoms that are bonded together. Good job, though, guys. Okay. So now that we know a little bit about greenhouse gases, I want to specifically talk about carbon. So carbon dioxide, like I said, it's the #1 gas or molecule that humans produce. And it's actually causing a lot of problems, not only with our atmosphere, but also with our oceans as well. So carbon is made from fossil fuels, from burning energy, from cars, from turning the sink on too long, to turning on a light. All those things emit or give off carbon dioxide that pushes up into the atmosphere. Now, carbon dioxide is a naturally occurring greenhouse gas, and we do need it to have life on Earth. But humans are creating so much of it by all these activities we're doing that it's causing climate change, which is making our Earth hot. Not only is our carbon dioxide getting trapped in our atmosphere, so let me try and find that picture again for you guys. So again, these greenhouse gases in the atmosphere right here, that carbon dioxide is getting trapped there. The sun is bringing its heat waves to bounce on and off those greenhouse gases, and it's getting trapped in the atmosphere, causing our Earth to heat. But not only is it getting trapped there, but actually about 30% of the carbon dioxide that is found in our atmosphere sinks down into the ocean. Now, if carbon dioxide is causing problems in our atmosphere and on land, do you guys think that it's also probably causing problems in our ocean? It absolutely is, and it is causing something called ocean acidification. So I want you guys to get out that worksheet that has different molecules on it. So you're going to have a water, a carbon dioxide, and then you have this page as well with a few other molecules. Oops, sorry. This page as well has a few other molecules on it. So there's a few ways we can do this activity. So for my atoms, I have lemons, I have some sweet potatoes, and I have some limes right here, guys. Okay. So I am going to have my H's, so like an H2O. So my H's to be lemons. So lemons right here. My oxygen, so my H2O or my carbon dioxide, which is CO2, my oxygen is going to be my sweet potato. Finally, my carbon, so CO2, so that carbon, the C in carbon dioxide, those are going to be my limes. And for the next part of the activity, like I said, there's 2 ways you can do this. One, you can place your food or items right on your atoms. So if you wanted to just place them on here, your O would be your sweet potatoes, your H would be your lemons or whatever you have. That's totally fine. And then you can just use the permanent marker to show you where those bonds are. But if you actually want to make molecules like this right here, this is my H2O. So I have my 2 hydrogen atoms and my O, my oxygen right here. I just used Q-tips and cut them to be my bonds. But after, if you want to try this activity, if you want to make it a little bit more challenging for yourself, you can use, like I used Q-tips, you could use straws, toothpicks, skewers, even like pasta noodles if you wanted to make your molecules. So we're going to start step by step to show what happens when CO2 or carbon dioxide reacts or like gets mixed together with ocean water. So let's just go over this one more time and you guys should say this after me. Carbon dioxide is in the air. So point up, carbon dioxide in the air, sinks down to the ocean. So carbon dioxide sinks into the ocean and mixes with water or H2O. And that is what is happening on this page. So you can see that there is an H2O plus a CO2. So what I'm going to do is I'm going to make my molecule. So I made this H2O right here. And then I'm also going to make my CO2. So I need 1 carbon, which is a lime, and 2 oxygens, which is sweet potatoes. So my carbon is going to be in the middle. So I'm going to take my lime, take my little Q-tips. Okay, so I have my 2 bonds, and then I have my 2 oxygens, so my 2 sweet potatoes. All right, just like this. And so you guys can see I made my CO2 right here. So you can put them down on your paper. So my H2O plus my CO2. So now these guys are mixing up in the ocean. So mixing, mixing, mixing. And when these things mix, molecules can actually change in order to become stronger, and especially when they see other molecules. So this carbon dioxide and this H2O are going to mix together, and they are going to create something called carbonic acid. So now, you guys, it might be a little bit of a challenge, but it'll be fun. Now you're going to make this carbonic acid molecule. So for this, you're going to need 1 carbon. So for example, mine is my lime. You're going to need 3 oxygens. My oxygen is my sweet potato. And you're going to need 2 hydrogens as well. So those 2 hydrogens right there, and that is my lemon. So if you guys want to, go ahead, either place them on the molecule that you have printed out or create whatever type of bonds you have. All right, so I have my 2 COs. I need made mine. I'll show you guys this really quick. So you can see I have my carbonic acid. So my 3 O's are my sweet potatoes, my lime atom is my carbon, and my 2 lemons are my hydrogens, and they are all bonded together. So now we have this carbonic acid and it's in the ocean. Now just think about the name for a second. Carbonic acid, okay? That's just something to keep in mind. So remember the name acid in the back of your head. Now, let's say that you guys are this carbonic acid and you're running around and you're creating so much energy and you're in the ocean and you're just going crazy. When you start to exercise a lot, or if you're running around, do you ever feel kind of tired or weak after and you just want to like lay down or just take a nap or something of that sort? Well, that's what this molecule is doing as well. It just worked really hard to get into this state, and to create all these bonds and all this energy, it actually becomes really weak, really tired, just like if you were to run in your backyard. And since it becomes so weak, it actually starts to break down in the ocean. And when it breaks down into the ocean, the hydrogen atoms go away and they become completely like by themselves. And the C and the 2 O's just stay together. So what we're going to do now, here, I'll try and lift it up and do it at the same time. So you guys can see I have my, let's see. Okay, I have my carbonic acid. It used up so much energy that now it's so weak and it wants to break. So now my 2 hydrogens are going to be completely by themselves. And one of my carbons is going to dissociate. And now, in the ocean, this we have left. We have 2 hydrogen atoms. They're actually called ions. Ion is another confusing word, but it's another type of atom. It's just very unstable. And then we have our carbonic acid right there. So I know that might have been a little bit confusing for you guys. That is the chemistry behind ocean acidification. But now you're probably asking, why does that matter? It's just a bunch of random crazy things that I can't even see in the ocean. Well, if you remember going back to our water quality lesson, there actually is something important of these hydrogen atoms or hydrogen ions floating in the water. And I'm going to bring back the pH scale. So remember the pH scale, it's basically just a way to measure water or to measure what is happening in any liquid that we might have. So ocean, the pH of 8 right here. So it's in the middle. It's not too acidic. It's not too basic. This is how corals like to live. This is how fish like to live. So a really healthy ocean has a pH of 8. But if we are creating something that is more acidic, so if we're adding, remember, carbonic acid to our ocean, carbon dioxide mixed with water creates carbonic acid, and all that acid is making our oceans way more acidic. These hydrogen ions that we have right here are collectively adding an acid in our ocean, and it's making our ocean water go this way on the pH scale. And this, guys, is not good. The more acidic our ocean gets, the weaker corals and fish and anything with a gets. And so I'm going to take you over here to show you guys exactly what does happen when our ocean becomes acidic. So like I was saying, there's tons of acids in our world, battery acid, even lemons are acidic. Our hydrogen ions are very acidic. Anything of that sort is acidic, including vinegar. So this is vinegar right here. It is very acidic, just like our hydrogen ions that we just did in our chemistry equation. So right here, we have a little bucket that I have filled with 2 of vinegar. And like I said, vinegar is acidic. So if I put a coral skeleton in water that is acidic, do you think it's going to do very well? Probably not. So let's put it in. So I don't know if you guys can see that right away, but all of that coral skeleton is bubbling. Bubbling a lot. Sorry, I'm trying to get you as close as I can. The reason those coral skeletons are bubbling is they're actually breaking down in this acidic environment. So we're going to pretend like this vinegar water is the ocean when it's highly acidic. So the same thing's going to start to happen in our ocean if we're using all this carbon dioxide. It's creating a more acidic, and our coral skeletons are breaking down. Now, let's say that 100 years from now, we don't really fix this problem. We decide, you know, I want to use more cars. I want to use more fossil fuels. I think it's super important to keep factories open as possible, to not turn off water when I'm brushing my teeth. All these things, the ocean is going to become exponentially more acidic. So now I have a piece of chalk. The chalk is going to represent really weak coral. So in 100 years, this is what's going to happen to our coral or our chalk that we have here if we are not careful and we don't lower our carbon emissions. So can you guys see what's happening to that chalk right there? That chalk is completely breaking down way faster than the first coral did. And this is because after 100 years, our corals are going to become way weaker and our ocean is going to become way more acidic, and it's going to produce a lot of problems for our coral reef ecosystems. So it's just really important that we remember that we can do stuff for our ocean right now. We can lower our carbon emissions, and this is something that we should definitely think about doing. So things as simple as turning off the light when you're not in a room is one of the things, and that's a really easy goal for anyone to do. So that is all I have for you today. Thanks for bearing with me with all the chemistry we were doing. I hope you guys enjoyed it. I hope you guys had fun. We will see you guys back on Monday